Scoochie everybody, it's AJ here, and in this video I want to talk about virtual memory. Now this video is about computer systems, and if you haven't seen my other computer systems videos, I highly suggest you watch them. But this video I will try to clearly explain what virtual memory is. Now the first thing I want you to imagine is the most basic building block of any kind of operating system or a computer. And the purpose of a computer is to be able to run processes. And as processes have gone along, you need to be able to execute multiple processes at one time to kind of do anything efficiently, right? When you're at your computer, you may have Chrome up, you may have Word up, you may have PowerPoint up, and you may have your text editor up to do multiple things. So what virtual memory allows you to do in correspondence with having a lot of programs done is it allows for each program, each process, which is a program, which is a currently running program, to be able to have its own area, or to be able to think it has its own area to run its process, store its memory, and read and write to data. And this is done by virtual memory. So as you can see here, I have four things. I have the CPU, which is the central processing unit, which does all the bit and byte and add and subtract and divide operations, kind of that's a low level or a very high level definition to make your program go. And then I have the MMU, which is the memory management unit, which I'll explain more in depth later. And then I have two things which you should be familiar with, which is your cache and your memory, which is your disk. So remember, you can access your cache a lot faster than your disk. So it's very valuable to have the blocks you need, or the pages as I'll call them sooner, to be able to have them in your cache rather than your disk, so you don't have to fetch them from the disk. And so that if you're always accessing the cache, that's called a cache hit, and so you don't waste all the time going to disk and fetching it there. And so what is happening again is that, let's just say in this context I have one program. What's going to happen here is I have my one program, my one process, and it's running here with all these things. And so I have a CPU which is running one process. And now my CPU, it's adding things, it's dividing things, or whatever. It needs, let's say it's going to need some memory. It's going to need maybe the location of a variable so it can store a variable. So what the CPU is going to do is it's going to go from the CMU to the MMU, which is the memory management unit. And what it's going to send to it is a virtual address. And the reason because it's a virtual address is the reason why this is called virtual memory, or VM. And the reason because it's called virtual memory is because it's virtual. Everything in this thing, everything that we're showing you does exist in the disk or the cache, but it's being virtualized to simulate, you're running a virtual machine, and that this process and its memory exists on its own terms. And this is very awesome and a very cool feature. So it sends this virtual address to the MMU. Let's say, for instance, it's 100. So it's going to send this virtual address to the MMU. And what the MMU is going to say is it's going to look at it, which is the memory management unit. It's going to say, okay, you gave me the virtual address of 100. Now, I can't give you the physical address of 100 because that is not what it's supposed to be. It's not supposed to be the virtual address of 100. It's supposed to be something else. So what I will do now is I need to find what the virtual address of 100 maps to physically. And because of that, I am now creating a mapping interface. And the reason because I'm doing this is because I am sending my MMU virtual addresses of 100 is because my MMU acts as a middleman. It says, I am not going to be able just to write to any location on the cache or the disk. It allows my MMU to translate for me, so if my MMU can't do the translation, it stops right there instead of doing something much worse and writing to the actual physical memory, which is very bad. So now I am going to go to the MMU and I'm going to go say, okay, hey, virtual address, I need to go I need to go figure out what this virtual address maps to. So to do that, actually, I'm going to go through the MMU, but the MMU isn't going to do the translation for me. What it's going to do is it's going to ask if I store, it's going to ask my cache for the page table. The page table entry is what it's called. So to, ask for page table entry. And it's asking for that because what it's doing here is, imagine my virtual memory is stored in a page table, which is simply just a table of entries. And what these entries do is these entries are stored at different parts in the memory. And at where they are in memory, what is stored at their places in memory is the actual physical address of where the mapping is. So I do that mapping. So that mapping is what's going to happen. And then once it figures out that mapping, time to draw another circle or another kind of line. Once it figures out that mapping, it sends back that page table address. And so when it sends back that page table address to the MMU, now the MMU says, okay, now that I've done my kind of lookup, I know where I'm located on disk. I know my physical address. I have now gone from my virtual address, which could be anything 0, 100, 2, 5, whatever, to my physical address, which may be 7,000, 8,000, definitely a different number. And now that I finally have that physical address, I can look it up. So now we kind of have a branch of things that can happen. So after going from, I go to the cache, I look it up, I go back to the MMU, and then I go back again to the cache with my physical address, and I say, is the physical address in the cache? Sorry I'm so bad at typing, but it's Gucci either way. So then I check, okay, is the physical address in the cache? Can you guys see that? So then I see, is the physical address in the cache? If yes, if it is indeed in the cache, then all I can do is I can just go, boom, I can go back right here. If it's a hit, if it's in the cache, that memory block is in this, I can just return to the CPU. Now the CPU has what it needs. But if not, then I'm going to go back. Then I need to go to disk, right? So imagine again, my cache is made into all these different blocks. Oh gosh. My cache and memory all made into all these different blocks, right? They kind of... I'll just divide it into 2 blocks for now, but you kind of get the message. I'll do 3. It's divided all into these different blocks, and memory ultimately has the storage for everything, but cache is much faster to access. So I want the most cache, I want the most used things in my cache so I can easily get them, I'm snapping my fingers right now. So, but if my physical address, what I want is not in my cache, I need to go to the memory and get it. And get from memory and then what I do is then I go back once I get it from the memory, because it will be in the memory, it must be, because I'm looking for it, and then I'll go back, and when I go back, I'm able then to find it in my cache. So when I did this process, that was kind of a bad example, guys. Well, that was kind of a bad explanation is what I should say. Is that when I realize I have a cache miss, it is a page fault. And when it's a page fault, I completely stop what I'm doing, and I go to disk. What I do is I go get it from memory, and then I get rid of a spot in the cache because I'm assuming my cache is full, and I get rid of a block in the cache. And I can use really any algorithm, or hopefully an optimized algorithm, to choose what I'm going to get from the cache. Optimally, the most optimal thing you can do, and there's no real algorithm for this, is to get the thing that will be used you want to get what's going to be maximally used in the future. So the thing that will be used the most in the future. So you want to get rid of things that you're going to use soon. You want to get things that are going to get used later. So you want to get rid of the thing that you're going to use later, or maybe never. So you would run your algorithm. You could do whatever, get rid of the first thing you used or the last thing you used, and you're going to replace that in the cache. So then you're going to put what you need in the cache, and then the MMU is again going to try to get it from the cache. And it's going to say, okay, well, now you're in the cache, I'm going to get it. And so then again, you follow this line and go back up to the CPU, and now you have your block. So that is what's awesome about virtual memory is really you want to know two things. You want to know that you can, first of all, conserve the cache, or you can bring the idea to any process that it's kind of encapsulated and not allow it to access bad regions of memory by kind of having the MMU serving as a middleman. What you can also do is that you can possibly share memory with other processes. So for instance, if you imagine here, if I had another CPU, it's not going to select for me right here, but if I have another CPU and I have another process running, kind of imagine everything is copied here, what I could do here is that all my cache is the same. I would have another MMU, but then that could map to the same things in memory. Let's say I have the malloc library or the libc library loaded in my cache. I could have another process pointing to the same libc.a folder or .o folder and extracting memory from that. But both of these processes would think they're completely separate, which is what you want to think. So you can share memory, and the virtual addresses will think, they're accessing totally different. I'll get rid of that. Are accessing totally different places, and it's its own space, but really they're sharing data, and so you don't have to copy that data over to another process. They can both share it in the cache, which is awesome and a really great thing of virtual memory. The last thing I'm going to add about virtual memory, since I'm just going on here and I might as well just keep going, is that it's possible that, so you can see that I have to go to the cache to get my page table, to get my table, my lookup table essentially, to find where it is physically, to then do my lookup to see if it's in the cache or if it's in the memory. Well, it is possible. Let's say if my lookup table is so big, let's say I have a huge application and all my virtualizations, my lookup tables will be a lot of memory too. It will be 512 gigs. So it's possible that your program could be so big that it has so many virtual addresses that you need kind of a huge table. You need a huge lookup unit. So what you're going to do here is that you're going to have multiple page tables. And what a page table does, if I didn't explain it earlier, a page table is simply something that has the pointers to where it is physically. So when I load a page table, I say, okay, it can give you, eight spaces or 8 numbers of physical addresses, and you can say of mappings from physical to other addresses. And so instead, if my page table gets extremely huge, what I'm going to do here is I'm going to have multi-tiered page tables. And what that would be like is that I could have one page table here, one page table here, one page table here. And what will actually happen is I'll have my main page table, which is all we've been talking about this point, is that I have my main page table, which has all my links to what I need in the cache. But since I need so much, what I'm going to do here is my main page table, instead of linking the physical addresses, is just going to link to other page tables. And those page tables, it could keep going on, but we'll just stop here. If I have even a bigger application, will then contain the physical addresses. And what this allows is, it allows for me to have a bigger page tables, bigger translation space for my bigger applications. Now, the thing about this is that my main table will always be certainly in cache because I'll be using it so often. But my hierarchy page tables may be stored in memory in the disk. So I may have to go get them. I may have to load it from disk, just like I have to load a physical address if it's not on the disk. So that's something to think about. So you may have to do kind of 2 loads at the same time. 2 loads just to get one physical address or one physical block, which could be really bad. But if you have a huge application, it's going to be slow. There are trade-offs to having a big application, and that's why you want to try to make it lower. I hope you guys enjoyed this video. If you didn't, tell me what you'd like to see. And I'll try to post some examples, but I hope you enjoyed this video. Have a great day. And my question of the day that I'll add on is, what is your favorite childhood moment?